Okay, let's continue on. When we left off, we were talking about water was more dense as a liquid than it is as a solid. And if you look at these pictures, you can see that water is a much denser structure as a liquid than it is as a solid. Liquid ice, as you can see, opens up and into this hexagonal structure, so we can see this crystal lattice, okay, and you have this regular repeating array of these water molecules in this hexagonal structure. So again, densest as a liquid, not as a solid. We know that ice will float on top of water. So that means that when a lake freezes, the lake does not freeze from the bottom up, but the lake freezes from the top down. And basically that ice acts as an insulator, protecting all of the life that is underneath the water, because the ice will actually float on top of the water. So that is another wonderful characteristic of water. Water also ionizes. Water, when we say ionizes, we could also use the word dissociate. So it breaks apart into two things. It breaks apart into hydrogen ions and hydroxyl ions. And when we, so water also will be it does help to make up pH. Okay? So acids, bases, and pH. We know acids have generally a greater number of hydrogen ions. Bases are going to have a greater number of hydroxyl ions. When we said water breaks apart, we end up with an equal amounts of hydrogen ions plus hydroxyl ions. Okay, we know that hydrogen ions, when donated to a solution, lower the pH, and hydroxyl ions, when donated to a solution, they raise the pH. And we're going to talk a little bit more about that when we start talking about pH. Okay, so what about pH? Acids and bases. So again, acids are molecules which release hydrogen ions. They release hydrogen ions in a water solution and drop the pH below 7. So you can see here below 7. Okay, now, then what are bases? We know that bases are molecules which release hydroxyl ions in a water solution, raise the pH above 7. But we want to add something else to that. We said bases are molecules which release hydroxyl ions, okay, but they also can or bind hydrogen ions and raise the pH above 7. So anything above 7 is considered a base. So we would write that less than 7, or we could either say below 7, or we can say, and that's an acid. We said anything greater than 7 or above 7 is considered to be a base. Okay? Now, let's keep moving. One of the things I don't want to say, if given the pH range, say for instance, this one is showing you normal pH range of blood and tissue is 7.35 to 7.45. So what if you had a pH of 7.25? What would you consider that to be? Good. If you said that's still acidosis, you're correct. So if you said, because some people get confused, because 7 and anything above 7, but now I said 7.25, they would say that's basic. No, for the range of this blood and tissue, that normal range, so we're always going to work around whatever the normal range that they give you, so we know that that's acidic according to the perfect range. All right, let's move on and talk a little bit more about pH and buffers. All right, so What is a buffer? A buffer is a chemical that's going to basically resist drastic pH changes. Our bodies have buffers that help us from shifting quickly from one pH to the next pH. So if the pH is too low, we know that we need to bind up some of those hydrogen ions and raise the pH above 7. We know if the pH is too high, we want to donate some of those hydrogen ions and lower the pH. The blood pH, again, we said it must be somewhere close to 7.35 to 7.45, so somewhere close to 7.4. If it's not kept between that range or somewhere close to 7.4, we know that that can be detrimental to health because the hydrogen ion is extremely reactive and it can nick up DNA, for example. Different radicals in the body, they can prove to do us some harm. So it says blood pH is below. The other reason why it's can be fatal, either below 6.9 or above 7.9, is the fact that we've got, say for instance, let's just use enzymes as an example. Enzymes are proteins. If you've ever heard anything about them, you'll learn more about them when we get to chapter 3. But in using enzyme in its three-dimensional form is when it's most active. It's when it has an active site. In its linear state, there is no activity. So if we, because of pH, damage the interactions because of the chemicals that we've exposed the particular enzyme to by our eating habits, drinking habits, whatever, it says that this guy can unfold into that primary state. We said in the primary state, the linear sequence of the amino acids, there is no active site. Let's see, can I draw my little cartoon drawing? But if we had an enzyme that had an active site and we've exposed it to extreme pH, for example, then we may end up unfolding that enzyme back into its linear sequence. So the first amino acid, peptide bond, next amino acid, peptide bond, so on and so forth. This has no what? Active site, so it's not going to be active. So we've damaged whatever chemicals, meaning proteins, macromolecules that have been active in the body because of the pH that we've exposed it to. All right, and that concludes chapter 2, and I hope to hope you guys tune in to the next video, which will deal with the macromolecules. Hope you have a wonderful day.